Welcome to the Nano Building. My objective today is to show you the facilities that will play a key role in the building of the silicon carbide fabrication facility. Basically, all of the equipment that we have are needed to produce good material, to analyze them, to turn them into a device. And so what I'm going to show you is first our analytic equipment that allows us to determine whether the material has defects or is a high quality, and then also some of our growth facilities that allows us to grow materials and process them. So let's first begin with our microscopes, which allow us to see at the atomic scale the structure of the material and lets us determine the quality of the material that we're working with. Okay, so this is our first stop. It's our transmission electron microscope, which allows us to see down to 0.7 nanometers. As a result, we can see individual atoms. And of course, if there are defects in the material, they'll certainly show up here. The microscope is in a room, by the way, that's a Faraday cage. It's sitting on a total vibration isolation structure. The temperature of the room and all of the rooms that I'm going to show you are controlled to within 1 degree. And all of this allows us to imagine taking a picture, for example, of a person. You want them to stay still while you grab the picture, but imagine a single atom. You're trying to take a picture of a single atom, and a little motion doesn't take much to make it a blurry picture. So this instrument is particularly useful when we're making devices, silicon carbide devices, because we could take cross-sections of this material and then analyze the structure, especially at the interface, telling us how good we're growing or how good we're making the material, or what the role of the interface is in the device properties. So in addition, this is again another Faraday cage, another room. Here we also have a environmental SEM and also a cryo-TEM. But in this room, we have a FIB, or a focused ion beam. This allows us to image the surface while we're writing on the surface with an ion beam. And so we use an electron beam to produce the image, and then we use an ion beam to write on the surface. And of course, this is particularly important if we're making devices or if we're exploring defects in a device, or trying to explore defects in a device. It's also, this focused ion beam also is equipped with cathode luminescence, which allows us to see, get optical properties from the material in a region that's much smaller than the optical wavelength, down to like 10 nanometers in 10 nanometer region. So we excite that region with the electron beam, and then we capture the fluorescence being emitted. This is great for studying nanostructures, especially silicon carbide nanostructures that we'll be interested in. Next stop is our growth facility. This is perhaps the best molecular beam epitaxy growth facility of semiconductors in the country. And it allows us to grow semiconductor materials one monolayer at a time. And so when we want to explore the quality of a material, this is particularly important because we could put down one monolayer, take a look, analyze it with a scanning tunneling microscope, which is on the other side, and that allows us to understand the quality of the surface and whether we're ready for the next material, a monolayer of a second material, and then a monolayer of a third material. So consequently, we build a material one layer of atoms at a time. So now we've moved to the other side of these growth chambers, and so what you're able to see here is really where the growth takes place. Earlier we were looking at a long chain of ultra-high vacuum. Vacuum is as good as a vacuum in space. In fact, if you calculate, you would calculate that one air atom would land on a surface in 8 hours. So basically when we grow, we can count on reliability of the growth of materials simply because there's very little impurities that can enter into the structure. The first end I showed you was really the transfer line, which allows us to move our substrate right down the line to any one of these growth stations. Then we move it into one of these growth stations, and that's where the growth takes place. Under high vacuum, under controlled temperature conditions and controlled vapor pressure conditions of the different kinds of materials that we're going to put down on the surface. So our next stop is our optical characterization room. So we not only want to grow the material, we not only want to look at it on an atomic scale, but we want to look at its optical and electrical properties. That's how we know if we're making progress in making a better material. So what you see here are laser systems that cover the range from continuous wave excitation of the material to femtosecond optical pulses that can excite the material in a very short time. And with a wavelength range or a color range beginning from the ultraviolet all the way out to the infrared, near infrared, at mid-infrared, actually somewhere around 7 microns. So this allows us to analyze solar cells, analyze detectors, analyze emitters. It allows us to make any optical characterization that we're interested in. And of course, silicon carbide has a number of questions that we want to investigate regarding its optical properties and of course its electrical properties. But here we can look at the lifetime of the excited state. We can look at the transfer of excitation, whether it's direct or indirect band gap, whether we're modifying the band gap by doping, all kinds of things, or by size, all kinds of opportunities to look at new optical properties of silicon carbide. Now we're taking a look at our electrical characterization. Of course, we want to know the mobility of the material. We want to know the carrier concentration. We want to know the magnetization of the material. This room gives us opportunity to explore all of the electrical and magnetic properties of the material. And so of course silicon carbide, if we mix it with other materials, this will provide us the opportunity to provide that analysis. This is especially interesting when we're trying to make sensors or we're trying to make transistors. All of these properties become important. We can do them all right here. Next stop, Ebeam Writer. Ebeam Writer is necessary to write on the surface with nanoscale precision. An Ebeam Writer is especially useful because it allows you to write over long distances without missing a stitch. In this case, we put down a material on silicon carbide and just write a pattern. And then, of course, we can take that material away and we can have the pattern that we're interested in down to around a few nanometers. So next stop, Xray. So in addition to looking at the atomic scale, we also want to get a bigger view of the overall structure of the material, how well the atoms are all connected together. What does the lattice basically look like? And so for silicon carbide, of course, we're going to do a lot of X-ray analysis on the material. And this gives us the capability. This X-ray machine has the additional feature. Not only can it do high resolution X-ray, but it also can do X-ray while we're changing the temperature of the sample. So for looking at low or high temperatures, we can analyze what's happening as a function of time as we heat the material, or if we are heating the material over a long time, like several hours, for example. This allows us, we can analyze a material for 2, 4, 6, 8 hours, for example, and watch what the changes are taking place in the X-ray pattern. Over here, in the same location, we also have another TEM. This TEM is not as high a resolution, only like 1 to 2 angstrom resolution. However, it's very easy for our students to take TEM very quickly, easy to be trained on it, and so this TEM serves the purpose of mass production of transmission electron microscope data. And so if the student is qualified, which is easy to do, then they can operate this on their own. Over here we have a confocal microscope, which allows us to do some imaging as a function of depth. Of course, it's particularly useful for biological materials, but it also has an added function, which is that it's two-beam confocal microscopy, meaning that two-photon excitation is possible. This allows us to penetrate materials that absorb ultraviolet, which most materials do, and use deep infrared radiation and two-photon absorption to excite those same materials in the ultraviolet region. Last stop, XPS, or X-ray photoelectron spectroscopy. In this case, we use X-rays, excite the material, and allow electrons to be emitted, and we measure the energy of those electrons. By measuring the energy of those electrons, we can tell what the material is. Why is this important? Well, because we're interested in the ratio. Let's say for silicon carbide, just as an example, if it's just silicon carbide, then we want to know, is the ratio of silicon to carbon 50-50, which it should be. This would allow us to determine exactly that ratio. Now, that's not so important for silicon carbide, but if we add other materials to silicon carbide and we're growing those materials, then we would want to know the ratio of material A and B to carbon, for example. So let me thank you for coming. I hope we've shown you the tools that we have that we can bring to the table for analyzing the quality, the devices that are made out of silicon carbide, and support the plan for this exciting silicon carbide fabrication facility. Thank you.